Welcome learners. In today's lecture, we are going to look into another kind of storage element known as capacitor. We are going to see the working principle of this device and what is the importance of this device whenever we apply this into various electrical and electronic devices. So before we begin, the image here shows various kind of capacitors available in the market inside various electronic devices. You might have seen these devices if you have ever performed simple lab experiments in your college classes or even at the university level. You might have seen the mostly used capacitors being the electrolytic capacitor. After that, the second most widely used capacitor is the variable one, followed by the film capacitors, and as we move on with devices that need complex and small scale elements, so we work with the ceramic capacitors, then we go to the polyester film capacitors, and then we have the circuit mounted devices or SMD based capacitors. So these are the practical capacitors that are available in the market. Again, it depends upon the application where you want to utilize them and which kind of size or dimension or footprint of the capacitor is needed. So you have these various available with you. So let us begin and see what is a capacitor and how the working of capacitor is done. So let us start first with the basic definition of it, or how is the understanding of capacitors that we have built. So as I mentioned, capacitor is an electrical component. Normally, its construction involves two conductors with a dielectric in between, or normally we say that it with an insulator sandwiched between them. And how does it normally works? It works by storing the electric energy. Sometimes you might read that it works by storing electric charges, but we will see shortly that charges are normally not stored, rather they balance out each other. So we stick to the definition of capacitor is an electrical device which primarily stores electrical energy. Charges accommodate that storage capability. Capacitor is the device other than the battery that stores charges. So normally battery, which we call as our power source, normally we write it as V of S. It can be dependent or independent, is similar in working to the capacitor with regards of the electrical storage of charges. So battery and capacitors are the two devices that basically store the electrical charges, or we say that they store the electrical energy. Remember that capacitor, although is storing and using that energy, is still a passive element. It's a passive element in the sense that it cannot independently generate energy, or it cannot supply energy. First, it has to store the energy, that we are going to see how, and once that energy is stored, it can then supply the energy, or we say we can retrieve that energy to perform various functions. So this is almost similar to the first storage element which we studied in our last lecture, and that is the inductor, which also is a passive element. And so inductor was also a passive element which basically stored the energy in the form of magnetic fields, and then that energy was used to produce the induced voltage, which later on worked with different objects. Similarly, capacitor is represented by this symbol, and we use a capital letter C to indicate its working. Basically works by storing the electric fields. Again, the polarities and the flow of current is dependent upon the passive sign convention for both the cases. Okay, so how does this electric field basically generates? So electric field is basically generated using the time varying voltages. So we are going to look into this statement as well. So time varying voltages basically generate electric fields, and these electric fields basically generate the displacement currents which flow through the capacitor. We are going to look into this phenomena as well. So now once we have laid down the basic statements of how the capacitor works and what kind of device it is, let us further understand its working principle. So there are different ways to understand the working principle of a capacitor. Let us look at both the scenarios. So the first scenario, or to understand its working, is such. So let us say I take any two conducting materials. So these are two conducting plates. This conducting plate or a conductor can be made up of copper, it can be gold, it can be silver, it can be aluminum. You can take any conducting material. So these are the two conductors that we have taken, and in between these conductors, separated by a distance d, we have what we called as an insulator. So insulator normally can be an air with a permittivity value of 1, it can be piece of paper, it can be mica, whatever material you want to use. It should be an insulator or a dielectric material in between these two plates. Now let us suppose that I connect these plates with a switch to a power source or a power supply or a battery. So this is our battery, this is the voltage terminals, and let us assume that the switch is in the on state. By on state we mean that the voltages is basically active, which is causing the charges to move from battery towards the conductor. So in this scenario we can see that the positive charges will start appear on the positive side and the negative terminal or negative charges will appear at the bottom side of the plate or the conducting plate. So if we take a DMM and place it over here to figure out what is the voltage available. So let us say we want to figure out with a measuring tool that what is the voltage appearing across these two terminals. So we might get a voltage of V1. So this is the voltage that is appearing. So interestingly, if there is a voltage available, how the current is going to flow, because these two conducting elements have an air gap represented by D between these two elements. So you might have read in your junior classes or physics courses that there is a phenomena associated with charges. So if I have a positive charge and I have a negative charge, we know that these at the atomic levels generate energy in the form of field lines. So positive charges originate the energy in the outward direction, which we called as electrical fields or the electric field, and similarly for the negative charge the fields are inward, so they basically absorb these field lines or the electrical fields. So same phenomena is mathematically represented that these fields or electric field E depends upon the applied voltage and the distance between the elements or the atoms in this case. So same condition leads us to the capacitors as well. When we start to measure the voltage V1 across the terminals, we find that there is certain voltage appearing, and this voltage, although being the air gap of D between these two elements or as an insulator, these are generated because a huge amount of positive ions are accumulated on the top side of the conductor and the negative ions are accumulated on the bottom end of the conductor, which means that the electric field will flow from the positive to the negative side, and thus this flow of electric field gives the displacement current or generates the displacement current, and thus the current is flowing through the capacitor. So the current flowing through the capacitor then comes out to be dependent upon this mathematical expression, which is I is equal to C dV by dt. We are going to further look into this very important expression, but at this stage we understand the first scenario, that whenever we have two conducting plates and we figure out that there is certain voltage V1 available. So in order to make sense of how the working principle is happening, we go back to the equation of the electric fields generated by the positive and negative ions, and this gives us the understanding of how a capacitor gets charged. So this is the point where the capacitor gets charged. Now let us see what else we can do with this. Now we take the same element or same conductor and now we close the battery. So let me draw these conductors again. So this is again my conductor, plate 1 and plate number 2, separated by a dielectric, let's say an air medium. And now I'm going to remove the battery source, or I'm going to open or switch off my circuit. So let us say that this portion is now not available. So there is no voltage supply being given to the conducting materials, and it already has a huge amount of positive and negative charges available on its plates. Now if we connect these two conductors to any load, let's say a load of RL, what is going to happen? So initially in the previous case, the capacitor got charged as shown over here, and now once the switch is closed, or in other said it is in off state, we see that no other charging is happening. So now the capacitor is going to discharge the excess number of charges which is available on its plate in the form of this positive and negative charges. So whatever is the load element over here, it is going to utilize those charges to function. If we have a normal load, it is going to heat up because the positive charge will flow towards the negative in the traditional way. And if we attach, let's say in place of this resistor, any electrical bulb, so it is going to glow. It is going to keep on glowing unless the excess number of charges that were available on these plates fade out. Once they fade out and reach back to their electrical neutral state or electrically neutral state, the glow will start to diminish, and then we will have a bulb that is just going to be there and it will not glow. So the glowing will conclude once the excess number of charges have stopped flowing through the bulb itself. So we see that capacitor has this natural ability to get charge and discharge. So capacitor basically gets charged first, and later on if we disconnect it from any external source, in our case a voltage supply, it is going to discharge the excess ions in the form of positive or negative charges. So this is the behavior or working of a capacitor that is very useful for us, and we have seen the applications of these capacitors in our daily daily lives. The best example is of that of ceiling fans. So whenever you start a fan, some of the energy gets stored, and when you switch off the fan, you still see that the fan doesn't immediately close, but it takes certain time to discharge those ions. If we take another example of fast working of charging and discharging, it can be your touch screens. So mobile touch screens or tablet touch screens are examples where capacitive touching is used. Obviously that consists of a combination of capacitors, but it does this works on the same principle of charging or discharging of charges. So this is how the capacitor is working. So now let us dig more into this. Okay, so this was the first scenario. We can understand its working with the second scenario as well. So the second scenario, to understand the working principle, is again we take two conducting materials, again let us say made of copper, and this time we say that what happens if we don't connect it. So initially we have what I mentioned now is the electrical neutral behavior. So what is the electrical neutral behavior? Means that whenever you take any conducting element, it already consists of balanced combination of positive and negative charges on each of the plates. So this plate will also have positive and negative charges and so on. So this condition is called electrically neutral. Now what happens when we connect this to a voltage source, again our battery having its own positive and negative terminal. So now let us understand the second scenario or working of the capacitor through the flow of electrons phenomena. Again this is an insulator in between, the air gap we can say, and let us use the concept of flow of electrons to understand how this gets charged. So let us assume that, or let us understand that as soon as we connect the battery, what is going to happen? So since this is the positive side, it is going to attract all the negative ions from the top conductor plate. So all these negative electrons will be attracted towards the positive side of the battery, and as soon as they reach over here, they are going to pass through this point, enter to the negative side, and again they will be pushed to the lower end of the battery. And similarly, more negative ions will get charged over here, and this positive elements which are available at the lower side of the conductor will be attracted towards the positive side, and they will go on the opposite side. But again, we are discussing the flow of electrons, not the traditional flow. So we are not interested in the flow of the positive ions, rather we are interested in the flow of electrons. So what happens is that the electrons which are available on the top of the conductor gets attracted to the positive side of the battery. They are then moved from the negative side. As soon as they enter this region, they get a push from the negative side, and thus they get accumulated on the bottom of the terminal or bottom plate of the conductor, and thus this process continues until and unless we start to build a potential difference of delta V between the top and the bottom conducting plate. So now how the electric field is going to be generated? So in order to cover this air gap, this point, we need to have strong charges available on the plates. So as soon as the potential difference becomes equal to the voltage supply, we see that the electrons and the positive ions are basically increased in numbers in such a way that the electric field starts to produce from the positive side towards the negative side. So the potential difference, whenever it reaches the supply voltage, we say that the electric field has been generated. And once the electric field is generated, we know that it is the ratio of the applied voltage and the distance between the elements, and thus this is going to generate the displacement current inside the capacitor. So this is the second scenario to understand how the capacitor normally gets charged. And again, if we remove the battery and connect it with any load, it is going to discharge the same number of excess amounts, and it will again reach back to its electrically neutral position. So this is how the second scenario works when working with capacitors. So now let us see further the performance metrics of these capacitors. So normally capacitor is measured in a term called capacitance. So as we saw before with inductance and resistance, capacitance is the term that measures the behavior of a capacitor in the sense that capacitance basically is the, we can say it is the ability to know how much storage of electric charge is available, or electrical energy or I can say charge the capacitor has. So capacitance is basically telling us that it is the ability of the capacitor to store electrical energy. So this is what we called as capacitance. So let us say if we have a capacitor, so this is the symbolic representation of the capacitor, and we apply a certain voltage to it. So we want to know that how much capacitance C1 is available at this capacitor, or how much the electric charge is available or stored in the capacitor. So we know that whenever the voltage is applied, we get the positive so let me write this as positive charges on the upper plate, and we get the negative charges on the bottom plate. So mathematically, capacitance can be figured out by writing it as a ratio of charges per unit the voltage applied, and the relationship to find the charge is equal to Q is equal to CV. So this is the mathematical expression that let us know that how much capacitance, which is the storage of electrical energy available at the capacitor, and it is nothing but the ratio of the charges per unit applied voltage. Similarly, there is another mathematical expression for capacitance, and that is associated normally when we include a medium other than air inside or in between the conducting plates. So it is with regards to a parallel plate capacitor. So a parallel plate capacitor is nothing but again two conducting plates. So let us say I have a parallel plate over here. So the name comes from its shape, it's a parallel plate, and in between we can have either air material or we can fill it with any dielectric material. Obviously this is the dielectric material. So it is going to have its property represented by the value of permittivity. So what is the parallel plate capacitor? Parallel plate capacitor is going to have its area, which is this whole area. Then we have the distance between these two plates and the permittivity. So in this scenario, we can further look into the capacitance and figure out that capacitance depends upon the permittivity of the material, the area that is covered by the plate, and the distance between the plates. So we can see from the mathematical expression that if permittivity increases or the area increases, the capacitance will increase, but if the distance increase, the capacitance will decrease. So this is the mathematical expression that further enlightens us about finding the capacitance with regards to any dielectric material in between the conducting plates. And we can see this as well from the image over here, that if this area A is increased by, what does it mean? That if we have more amount of charges in a expanded area, so the capacitance, which is the ability to store electrical energy, is going to increase. Similarly, if the distance, which is from this point, is increased, then it will take more time for the electric field to form. Electric field to form means that movement from positive to negative ion will take more time, thus the capacitance will decrease. On the other hand, if we talk about the permittivity, which is the dielectric material, the more or the higher value of permittivity, the more will be the capacitance, because permittivity is going to force the electric fields to have more elements. How it is going to happen? Let us look into the permittivity aspect of it. So if the permittivity, which is the material's property, is increased, the capacitance is increased. So let us assume we have these two conducting elements, and in between I have a dielectric material over here. So what is a dielectric material? So if we talk about the permittivity, you might have read about its value. In free space, its value is 8.85 into 10 raised to power minus 12 farad per meter, farad being a unit of capacitance. So this is the value if you are using a free space material, which means an air gap between them. But if the material is changed, the value of permittivity, which is E naught, is also going to vary. So let us say if I take any dielectric material, how the capacitance is going to increase. So when we have a dielectric material in its ideal state, so in an ideal state, the dielectric material means that this material has two atoms per area. So this is, these two atoms are combined in the group. You might have these two atoms combined over here. So these are randomly placed inside this dielectric material, which we also called as an insulator. And we know that in ideal case, the conductors are electrically neutral. So it is going to have positive and negative charges on the top plate, and then negative and positive charges on the bottom plates. As soon as we connect this to a voltage source, let's say this is positive and this is negative, what is going to happen? So we already have seen that the negative ions will disappear from the positive side. So the negative ions will start to flow over this side, and similarly on the bottom side, positive ions will also be disappeared. The only thing we are going to be left with is going to be the negative ions in the bottom plate and positive ions on the upper plate. What happens to the dielectric material in this case? So as soon as the voltage is applied, the dielectric material is going to shift its polarity. So since we have negative on the upper plate, the random elements over here will be refigured or reconfigured to something like this. So previously the elements were ideally or randomly placed. Now since we have higher value of electric field on the top of the conductor and negative value on the bottom side or the excess of ions, So here, and these two basically wants to generate the electric field, but because of the dielectric material, what is going to happen, that the negative and positive will form in such way, and this is the pair inside the dielectric material when it gets excited by the external source. And in this way you can see now the element or the dielectric material over here, the dielectric is trying to resist the formation of this electric field, because an internal electric field is made over inside the dielectric material, which we can see from here. So again, the original is moving from here to here, but inside the material another electric field opposite to the original electric field is made, which is basically opposing this electric field to be formed, which and thus means that the current is having difficulty to be generated, or the displacement current is having difficulty generated. So in order to cope this, the battery is going to supply more and more of these positive and negative ions, and thus these are going to overshadow these smaller or local electric fields inside the dielectric medium, and thus we are going to have the formation of an electric field. So since the electric fields has been increased because of the additional amounts of charges, so the capacitance has increased, because we said capacitance is the ability of capacitor to store electric charges, and electric charges have here increased abundantly. So this is how increase of permittivity value increases the capacitance value. I hope this idea is clear. But important thing again is we need to know that what is this equation and what is the importance of these two equations as well. So now let us further see into the current and voltage relationship of the capacitor. So now let us see what is the current and voltage relationship for capacitor. So we know that from our prior knowledge that current is the rate of change of charges per unit time. So if we take any capacitor and we apply a certain voltage, we know that the current is going to flow through it based on this mathematical expression. And we also know that charges are basically creating the capacitance due to the applied voltage. So we just input the value of Q in the equation of current. So the current value comes out to be C dV by T, and this is the main equation for capacitor. So this is a very important equation which we are going to discuss now. So this is basically telling us that how much current or displacement current is produced whenever we use or capacitor for discharging the current. And we also want to know that what is the relationship between, or what is basically this equation trying to say. So let us plot the relationship graph between the current and the rate of change of voltage. So so the relationship between them is always a linear line. We try to maintain, or the capacitor tries to maintain, this linear relationship between voltage and current. What it means, or what this equation 1 means, is that this equation is like a balancing act equation. So balancing act means that whenever the voltage tries to go to a maximum value, the current inside the capacitor is going to come down to a smallest value or to the zero value in order to maintain this linear relationship. If not, then the system will not function properly. So that's why we say it's a balancing equation, because whenever the value of voltage increases, the current brings it down, or the capacitor drains the current in such a way that the value of current goes down to the minimum value. Similarly, if the voltage goes down to a minimum value, the capacitor increases the current by utilizing it in such a way that the capacitance behavior remains as much balanced as possible. So this is the importance of this equation. And another thing that we need to keep in mind with this relationship equation, especially for capacitor, is that we have seen in case of resistors that the Ohm's law is applicable. Ohm's law says that V equals to IR and V equals to I if the resistance is a constant value. So if the voltage is equal to 0, then current is obviously going to be 0. But what about in case of capacitor? So in capacitor, you have to remember that you might see these scenarios that sometimes the voltage is not 0, but the current is 0. In other scenarios, voltage is 0, but the current is not 0. Now how this thing can happen, it's very simple. Let us say I have a capacitor and it has now been charged, and I have removed the battery and there is no connection. So now the capacitor is holding certain voltage, but there is no flow of current because I haven't connected its terminal to any other device. So you can see it's an open circuit over here. So the current cannot flow between terminals, let's say A and B. So this is one scenario where you can see that the Ohm's law is not applicable, but the capacitor has this innate ability where the voltage exists but the current cannot flow. Similarly, in second scenario, let's say if I have any systems whose behavior is such that this is my voltage, and what happens is now the voltage is 0 but the current is not 0. So you might have a scenario certain like this. So you can see at this point the voltage is having a value of 0, but these points the voltage is changing. So again remember that dV by dt is not 0, but the voltage itself at this point is 0. The change of voltage is happening as can be seen from these two values. So this is another thing to remember. So for capacitor you might have both the cases, that where one is having a value and other is not, and vice versa. So this is the example that we are having. Okay, now let us come back to equation number 1 and see what else information we are getting from this important equation. So the information that we are getting from this is such. So if we have a capacitor C, and let us say if we apply any voltage to that capacitor, so remember we need to apply the passive sign convention to find the value of Vc and the current accordingly. Okay, so this is what we'll see shortly. But anyhow, let us see what this equation is saying. So let me write this equation again. So this is the equation for finding the current flowing through the capacitor. If you have a capacitor C1, so it is dependent upon the rate of change of voltage. So as long as the voltage is getting changed in a linear fashion, the current is going to exist. But what are the scenarios that we normally face? So the first thing is that if in this mathematical expression, if we have a constant voltage, not a zero voltage, so value of voltage is not 0, but rather we have a constant voltage which we say as a DC source. So what is going to happen to the current? Obviously the current will be 0. So this means that whenever we have a constant voltage source, capacitor's current will be a 0 value, which means that whenever you apply a DC source to any capacitor, so if this is a capacitor, you apply a DC source, the output will be an open circuit. How open circuit? So we can see that the performance of capacitor is normally measured in terms of a value or a variable called the reactance. So how the capacitor reacts to certain inputs. So the reactance of the capacitor is mathematically given as 1 divided by 2 pi fc, where f is basically taken from the angular frequency, or it is 2 pi f is the angular frequency. But when we say that we have a DC voltage, which means that we have a constant source. So how the DC is presented? So you should remember this, that the DC voltage is something like this, a flat value. So in terms of frequency, it means that the value is 0f, or f is equal to 0. So when you do this, you get an infinite value. This means that the reactance of the capacitor, or the behavior of the capacitor to an input of a DC source, is basically infinite, which is an open circuit. So this is why we say that whenever a constant voltage is supplied to a capacitor, it behaves as an open circuit because its reactance is mathematically showing to have an infinite value. So this is the first point that we need to know, which is mathematically proven. The second point that we need to understand is how the balancing equation is working. So basically this is dV by dt, which is the rate of change of voltage, and as I mentioned, capacitor basically balances this rate of change with increasing or decreasing opposite to the value of current opposite to the voltage. So the value of voltage is maximum, capacitor will bring down the current to the minimum value, and vice versa. So let us say that if we have a voltage for a capacitor, so for a capacitor, as we saw with inductors, the abrupt voltage change, or we say instantaneous voltage change, or we say that jump from 0 is not allowed. or we need to avoid this condition, because if we don't avoid this condition, then our output current based on this mathematical expression will go towards infinity, and we don't have real systems that can give you infinite current. So whenever we are dealing with currents in capacitor, we have to see that it should follow this linear relationship where there is a linear change of current and voltages rather than the linear change, sorry, this should be a linear relationship between the change of voltage, so that we get a measurable amount of output current. There shouldn't be any abrupt change or zero jump. So what does it mean? Let us look into this further. So for a capacitor, we should avoid abrupt change, because if we don't do so, we are going to get an infinite current, and which is not possible in the real world scenario. So let us say, well, let us understand this point and also understand what is this zero jump. So let us say I have this behavior of a system, or the output response, or V out of the system, and we see that it is something like this. So I can have any value 0, 1, 2, 3, 4, and the maximum value is 1. So we can see that beyond the 0, 1, we have a flat line, and then there is a sudden jump, and this is the jump which I am talking about. This is a zero jump. So at point 0, you have immediately jumped from the 0 scale to a maximum value of 1, and this creates problem in case of the current, because it reaches an infinite value. How? So if we mathematically write this graph into a mathematical expression, this is nothing but an output voltage multiplied by a unit step function. Let us give it any variable V. So what is this unit step function? So unit step function is something whose behavior is such that it gives you a value of whenever you have time axis greater than or equal to 0, and it gives you a value of 0 whenever your time axis is less than 0. So if you look at the figure, if you have a value of 0 or greater than 0 in the time axis, your value is 1, and if you move in the time axis from 0 or less than 0, you will see that the value is 0 over here. So this is what the unit step function is saying. Now if we put the value of V unit step function into the equation of the current, so we know that I is equal to C dV by dt. We know that dV by dt is basically V out. You basically put unit step function and differentiate. So the differentiation of the unit step function, V naught being this, comes out to be an delta function, and this is the output that we are getting. Now what is this delta function? So delta function is called as an impulse, or a direct delta function. What does it mean is its behavior is something like this. So at only the instant of 0, you are going to get a maximum value. Other than that, on the horizontal scale, you have a 0 value. So the impulse function is such, at 0 instant you are going to get its maximum value. The maximum value is normally an infinity, and other than that, on the horizontal axis of any value of 1, 2, 3, minus 1, minus 2, 3, you are going to get a 0. So if you look at this and draw this output over here in the form of current, you can see at 0 value, where there was a sudden jump, we get an infinity of current, and this is what we want to avoid. So for a capacitor, we don't allow the abrupt change of voltage or a zero jump, because it is going to give us an infinite current, and which is not possible in real case scenario. So hopefully these two conditions are clear, and these two conditions are very important. Apart from that, our main equation to find the current is this one. Again, this is a balancing equation where rate of change of voltage is balanced out by the current drawn or extracted by the capacitor. And these are the 2 points that we have discussed, that a constant voltage generates an open circuit condition for the capacitor, and we avoid the sudden jumps, because if sudden jumps is going to give us infinite current, which is not possible in the real world phenomena. So now that we have figured out the current, what is the voltage that is appearing across the capacitor? So obviously we can just use the integration. So we know that the current was C dV by dt, so the voltage is going to be just the integration of this current. We are going to have, let's say, from minus infinity to a certain point, I of t dt, plus we go from t naught to t I of t dt, and as we saw with inductors, this is basically your initial condition. Again, we are going to talk about this in our coming lectures, that what is the initial condition, and this is your transitioning current or transition state. So we are going to look into the steady state and initial condition. So we can write this equation as the initial voltage that was stored in the capacitor plus the current relationship of the current that is moving through this capacitor dt. So this is the equation of the voltage that we are going to use whenever dealing with finding the voltage for the capacitors. Again, these solutions become more complex as we proceed further, but we are going to discuss them in our upcoming lectures. Finally, we are interested in the energy stored in the capacitor, because in the beginning we defined the capacitor to be a device that stores the electric energy. So in order to find energy, we know that it is the integration of power with regards to time, and power is equal to V into I. We know that the current is C dV by dt, so the energy comes out to be half CV square. So this is the important equation that we need to know, that in order to find the energy of any capacitor, it is going to be half CV square, and the equation is almost similar to what we saw with inductor. For inductor case, the energy was half Li square. So you can see the similarities between the storage devices, and this is the energy that we are going to find. Finally, let us talk about if you want to use certain values of capacitors that are not available in the market. So what can we do about that? So we know that we can use the combination of these capacitors as we saw with inductors and resistors. So this is basically the series and parallel combination for capacitors. So we saw previously that for capacitor, for inductor, we saw that the equivalent equations for inductor were similar to that for the resistors, but in case of capacitors, the equivalent is going to be inverse of what we saw for the inductors. So this is going to be an inverse relationship. What does it mean? So let us take the scenario where we have parallel combination. So in parallel combination for capacitors, we consider a current source connected to, let's say, capacitor number 1, capacitor number 2, capacitor number 3. So this is my current source, this is C1, this is C2 and C3. So we know that if the current is going to be different, so this is IC1, IC2 and IC3. So if we apply KCL, what is the equation that we are going to get? So we know that sum of currents entering is equal to sum of currents leaving. So IC3. So IS comes out to be, what is the equation of current? So current is C dV by dt, let us say C1, plus for the second it is C2 dV by dt plus 3 dVt by. Why it is dV by dt? Because the voltage remains the same in parallel combination. So finally we can say that the equivalent capacitance in parallel combination is the sum of all capacitors available, and this is opposite to what we saw in the inductors and resistor combination. So this circuit can be represented by a single current source and then an equivalent capacitance over here. So this is what we basically got for the parallel combination. Okay, what about the series combination? So in series combination, it is again going to be the opposite. So we have a voltage source and we have 3 capacitors, for example, connected in series. So we know that the current is going to remain the same and the voltage is going to be different for all this. So it is going to be VC1, VC2, VC2. So if I apply KVL to this circuit, I can write that Vs is equal to VC1 plus VC2 plus VC3, and I know that the voltage equation is going to be 1 by C integral. I can just write V naught T plus integral I of T dt. So this is the same equation which we found over here. So this is for the first condition. Similarly, I can write for the VC2 second condition, this is C1, this is T2, again it is V naught T. If I remove, sorry, the integration is not here, this is something like this, plus I2 dt, and similarly for the third one, V naught T plus I3T dt, and finally we can see that the equivalent capacitance for the series is opposite to what we saw with the inductor. It is going to be 1 by C1 plus 1 by C2 plus 1 by C3, and the rest of the equation will be we can say V naught T plus, let's say, In of T dt. So this In is normally uh, I1 plus I2 plus I3. So this is the rest of the equation, but we are mostly interested in this equation, which is the equivalent of this one. Okay, another thing to note for the series connection is, since we are having the equivalent, if we have two capacitors connected in series, so their equivalent is going to be C1 C2 divided by C1 plus C2. So this is we need to remember, because it helps us solving these kind of complex networks where multiple capacitors are needed. So to summarize this, the series and parallel combination of capacitor is opposite to what we saw in series and parallel combination of inductors and resistors, but the process of solving remains the same. So if I want to summarize what we learned in terms of a comparison, summarize, or a summary, or a comparison, to be more specific, comparison between inductor and capacitor. So what is the similarity and what is the difference elements? This is inductor and this is capacitor. So the first thing is that inductor is basically it stores energy magnetically, which we saw based on the Faraday's principle. Capacitor, on the other hand, stores energy electrically through the formation of the displacement current because of voltage and electric fields. Second point is that the linear inductor is basically formed by the relationship of magnetic flux inductor into current. So this is the mathematical expression which we saw. And for capacitor, the mathematical expression that governs this is basically the charge voltage relationship. So we have Q is equal to CV. Similarly, if we have a DC source, then inductor is going to allow the circuit to work in the form of a short circuit. But if we have a DC source, then capacitor doesn't allow the current to flow because capacitor works as an open circuit. So these are the two things that we need to know. Number 4, inductor basically opposes the change of current, and capacitor basically opposes the change of voltage. So what they do is, this is basically the balancing equation. So change of current means that we know that voltage is equal to L di by dt. So this is the change of current that is happening. So the voltage is trying to balance it. Similarly, for capacitor, the equation is that current is going to balance the change of dV by dt. So this is what it means by these 2 points. And finally, this change is basically for inductor mathematically represented by its reactance, which is J omega L, which is J 2 pi FL. So since there is a DC current, frequency is 0, so which means that XL is equal to 0 value, which means that the current can easily flow through it, a short circuit. On the other hand, the reactance is open circuit because the frequency is 0, so this is an open circuit value. And finally, for inductor, the stored energy is happening because VL equals to 0 volts. VL equals to 0 volts because the current is a constant, so VL becomes equal to 0. And for capacitor, the energy gets stored, the electrical energy gets stored when the current is 0. And we have seen this, that if the capacitor is charged, V is not equal to 0, but the current becomes equal to 0, and this is the point where it is getting stored. So these are the comparisons between these two storing elements. The first one onto your left is the inductor and the second one is the capacitor.